In the previous video, we saw some basic terminologies that are used in measurements. These are the static characteristics. You need to understand those concepts in order to understand whether the device is good, whether the device is reliable, how much it is reliable and all. So if you forget to watch that, quickly check it out and then come back here. We are going to solve some problems in this video. Let's get started. The dead zone in a certain pyrometer is 0.125% of span. The calibration is 400 degrees Celsius to 1000 degrees Celsius. What temperature change might occur before it is detected? In this question, it is given that the range of the pyrometer is 400 degrees Celsius to 1000 degrees Celsius. The span is 600. It can measure a span of 600, which is from 400 to 1000 degrees Celsius. So the span is given as 600 degrees Celsius. Next, it is given that the dead zone is 0.125% of span. What is asked? We should find out the temperature change that might occur before it is detected. It is given that the dead zone is 0.125% of span, meaning that from 0.125% of this span is going to be dead, or in other words, the instrument is not going to respond up to certain degrees of temperature, and that is given by dead zone, which is 0.125% of span. What is 0.125% of span? It is 0.125 divided by 100 times span. Span is 600 degrees Celsius. So the dead zone is given by 0.125 into 6, 0.75 degrees Celsius. So I think this is a good device because it is measuring a span of 600 degrees Celsius and the dead zone is just 0.75 degrees Celsius. So this is a better device actually, because only for this amount of temperature the device is going to be dead. And after this, or after 400.75, it's going to be a good device. Okay, so the dead zone is 0.125 of span, which is 0.75 degrees Celsius. So this device will begin responding at 400.75 degrees Celsius. Let's solve another problem. A digital voltmeter has a readout range from 0 to 9999 counts. Determine the resolution of the instrument in volt when full scale reading is 9.999 volt. In this problem, we have the range of the digital voltmeter. We have the range of the digital voltmeter, which is from 0 till 9999 counts. Okay, so meaning that this display will have 4 LEDs like this, which will show the reading from 0 till 9999. That is what is the meaning. And what is given? Determine the resolution of the instrument when full scale reading is 9.99 volt. The full scale reading or FSR is 9.999 volt. So this shows that this device has a precision of 3 digits. Even though it can measure from 0 till 9999, it is not measuring voltage from 0 till 10,000, or it is not measuring voltage from 0 till 9999. It's measuring a full scale reading only of 0 till 9.99 volt. This shows the precision of the instrument. Okay, so let's leave all the stories. We'll come to what is asked. We are asked to find out the resolution of the instrument. Okay, so this is a digital meter which can be measured up to 9999 and the count or the voltage corresponding to it is 9.99. You got your answer here because it is said that it is the maximum reading is 9.999 and the maximum counts is 9999. So one count will be 9999 divided by 9.99. right? Because if 9999 counts correspond to this voltage, so what is the voltage that will amount to one count? That is 9999 divided by 9.99, which is 0.001. So one count says that it is 0.001 volt or 1 millivolt. So the resolution is nothing but 1 millivolt. This device can count up to 1 minimum. Okay, so one count corresponds to 1 millivolt. So resolution is nothing but the minimum amount of voltage that a device can detect, and this count is 1 millivolt. So the resolution is 1 millivolt. A Wheatstone's bridge requires change of 7 ohm in the unknown arm of the bridge to produce a change in deflection of 3 mm of galvanometer. Determine the sensitivity. Also, determine the deflection factor. I hope you all would have known what a Wheatstone's bridge is. But you don't have to know all that in order to solve this problem. You just can imagine that Wheatstone's bridge is nothing but a resistance measuring device. When the input is resistance, the output will be movement of arm of galvanometer. The arm of galvanometer moves. You just have to be informed of this much in order to solve this problem, because you are asked to find out the sensitivity and deflection factor. What is given? A change in resistance of 7 ohm is giving a change in the reading by 3 mm. Okay, so what is sensitivity? Change in output divided by change in input. So sensitivity will be 3 mm divided by 7 ohm, which is 0.428 mm per ohm. So it means that for every 1 ohm change, the change in the arm or the change in the galvanometer's reading will be by 0.428 mm. This is what is sensitivity. We are asked to find out the deflection factor. What is deflection factor? How much should the resistance be for every one division of the reading, which is nothing but inverse of sensitivity. Okay, so the deflection factor is also called as inverse sensitivity. So what is deflection factor? It is 7 ohm divided by 3 mm, or just the inverse of it. So if the pointer moves by 1 mm, it means that it is 2.33 ohm added to the resistance. When the arm of the galvanometer moves by 1 mm, then the resistance is 2.33 mm. If the arm moves by 2 mm, then you can find out 2.33 ohm into 2, which is the resistance that is applied at the input. So this is deflection factor. We solved some easy problems in this video. You can practice similar things, and in the next video we are going to discuss about the signal to noise ratio and some problems based on this. Thanks for watching. If you like this video, do give a thumbs up and subscribe to my channel for more updates. Thank you.